little section on your notes today where we're going to look at just the solid state of matter. Solids aren't really that exciting, to be totally honest with you. They don't have a whole lot of vocabulary that's just specific to them. We have a lot of definitions and things with gases. We're going to have an entire unit with gases. We have the liquids, and we were learning about the intermolecular forces and what makes a liquid stick together. Solids are stuck in place. So if I have this tablespoon, plastic spoon here, it's stuck. There's no particle movement other than the little particles are just moving in place. So they have a definite shape. It doesn't matter if I put this down on the table, if I put it in the air, if I hang it from the ceiling, no matter what, it's going to keep its shape. And that's because the intermolecular forces in a solid are the strongest. So we have a gas that has no intermolecular forces. Then we have an intermolecular force to turn it into a liquid. The particles can move past one another, so their intermolecular forces are actually fairly weak in the liquid state of matter, but things get colder and the intermolecular forces strengthen. They get colder and the intermolecular forces strengthen more. And then finally you have the solid state of matter that have the strongest intermolecular forces that have these particles that are stuck in space, and all they're doing is just wiggling next to each other. So they're constantly moving, they're constantly vibrating, they constantly have energy, but they're not moving past one another. So they have a definite shape. That means that no matter where you put that solid object, it's going to keep its shape. A liquid will change its shape no matter what. Maybe it's very viscous, it does it very slowly. However, it will always keep its shape if it is a solid. If it changes shape, it's a liquid. So with your intermolecular forces, again, they have the strongest of the intermolecular forces, and they're holding everything together in place. Maybe it's not moving. There we go. So with your particles, this link does not work. It's a broken link. I need to delete that. But the particles that are there, just like what the kinetic molecular theory tells us, that you have particles that are always in motion as long as you're above 0 Kelvin. The particles that are there are very, very, very tiny, and the movement of those particles is dependent on the temperature. The higher the temperature, the faster the particles move. The lower the temperature, the slower they move, until you hit 0 Kelvin, and at 0 Kelvin, all energy in motion stops. Liquids and solids are also similar because they both have intermolecular forces. Gases have no intermolecular forces. Their particles do not stick together. Don't know why this is struggling to go to slide. Now, typically when we were talking about the density, we said that a density of a gas is very, very, very low. And then when you jump to the liquid state of matter, that density jumps up a lot. Normally, in a solid state of matter versus a liquid state of matter, your density is going to go up more. Meaning, normally, if you have a liquid of whatever substance you are dealing with, like rubbing alcohol in this case right here in this picture. If I have liquid rubbing alcohol and I have a frozen block of rubbing alcohol and I drop that into the liquid, the solid should sink to the bottom because it has a higher density. But water is weird. Water has polar bonds, it has hydrogen intermolecular forces, and when they come together, they actually make these intermolecular forces, not intermolecular forces, these little crystalline shapes that look like the ones in the picture that have little holes in them. And with all the little holes that are in them, there's open space here, and that open space that I have here allows the water to float in the solid state of matter. So these things, when they come together, they have a hole. That hole is not there when it's a liquid. So because it has that hole in the crystalline shape, it floats to the surface. So that's beneficial for animals that are in like a lake. If you live on a lake in Wisconsin, the top part of the lake freezes, but then the little fishes are swimming around. The little fish, are swimming around underneath that ice, and they're just kind of cruising around. So it allows for animals to still survive, even though the whole body of ice, or a whole body of water, isn't frozen ice. If this wasn't the case, what would happen is the top surface would freeze, it would sink to the bottom. Top surface would freeze, it would sink to the bottom. Top surface would freeze, it would sink to the bottom. And your river, lake, whatever, would actually freeze from the bottom up. So eventually the whole thing would freeze and you would kill all the animals that were actually living inside of there. So it's one of the cool adaptations that allows for life to happen on Earth. So there's two different shapes of your crystalline solids, two different shapes of your solids. You have crystalline solids and you have amorphic solids. For your two different types, it depends on how the particles squish together. If they have repeating patterns, you're going to have a crystalline shape. If the particles just squish together as close as they can, kind of willy-nilly, those are amorphic solids. So crystalline solids are actually called crystal lattices, and we talked about these with your formula units when we were talking about ionic compounds. We looked at table salt like we have here. Gemstones, this is an emerald. You can see the little square shape. That's because the way that the particles arrange themselves. The gemstone here, the emerald, the way that the particles come together, you could only cut an emerald in a certain shape. It's actually called an emerald shape, because of the way that the particles are all arranged in that solid, because it is a crystal. I actually have a different crystal here. I don't know how well you're going to be able to see this or not. Well, hang on. There we go. When we were moving from the old school to the new school, I got the lovely task of going through all of the old chemicals and looking to see what do we need to get rid of. And so when I was going through and trying to figure out what I needed to get rid of, I was pouring out liquids safely, obviously. And some of them I had to neutralize, and some of them I had to have a chemical company come and pick up and figure out what it was. Some of them weren't even labeled because the labels were so old. But this one, when we got rid of all of the liquid that was inside of here, this crystal had formed in the bottom because it had been in the container for so long. And I don't know if you can really tell that shape or not, but it's got some really cool crystalline shapes to it. So I kept it because, like I said, it was just pretty cool. Now I did have another one, but I don't know where I set it down. It's not going to make this video. Sorry. I had another little bottle that I had found when we were cleaning out a medicine cabinet at my grandparents' house. It was an old syringe bottle, but I'm going to be honest with you, I don't know where I set it down. I thought I put it on the table up here with the purple one. So crystalline solid just has these repeating patterns that everything comes together in a set way. Your crystalline solids are going to have your highest intermolecular forces. They're very, very, very strongly put together because you have the opposites attract, they're sticking together. That means that they do not want to change their arrangement. So they don't want to change from one state of matter to another. So they don't want to go from a liquid to a gas. They don't want to go from a solid to a gas, or from a solid to a liquid, or whatever else. Your crystalline shapes are going to have very high melting points, and then when they eventually turn into that liquid, they don't want to actually turn into a gas either, because those strong intermolecular forces are holding them in place. Now an amorphic solid is kind of like this putty that I have here. I made the putty into a little square shape here, it's a little cube. But I can take the putty, which is a solid, and I can squish it. And I can make it into whatever shape I want to. Now when I make it into the new shape, when I leave it sit on the table, it's going to keep that shape, whatever it is. So I could roll it into a ball, and all I'm doing is I'm just changing where those particles are actually arranged. But I changed it from a cube into a round little ball, and it's going to hold that shape. So it is a solid, but it's an amorphic solid because I can shape it however I want to. Your amorphic solids are going to have very weak intermolecular forces. They're going to have very low melting points, so they go from a solid to a liquid at a very low temperature. So if you have plastic, it's very easy to melt plastic. If you have glass, it's actually pretty easy to melt glass. In a normal year, at the end of the year, we would do some glass bending. I don't think that's going to happen this year. But you have these different compounds that come together and they form a solid. When they form that solid, they just have their particles just kind of arranged however they want to. When they break, like this glass, they just shatter. There's no rhyme or reason as to why they break the way that they do. They don't have to break along a set plane. And that is actually all that we have over solids. Like I said, it was going to be pretty short. There isn't a whole lot in terms of the vocabulary for a solid. We don't spend a whole lot of time on them. We really focus our time in on the liquids and the gases. So if you guys have any questions, make sure you ask. My email is mgable@crosbyisd.org. Otherwise, have a great day.